Hello everyone, this is the Jutian team from China Mobile Research. I'm very happy to share our recent work today. In this paper, we are motivated to systematically study the code-switching behavior with a large Mandarin-English speech corpus. The analysis is organized into three levels: phonemes, words, and context of the CS segments. On each level, we investigate the features of the distribution, pronunciation, syntax, and semantics of CS segments. We run quantitative evaluation to measure how these factors influence CS and reveal certain commonalities. The findings in this study are complementary to direct CS modeling and can be used to further guide the enhancement of model design. The data-ton Mandarin-English corpus is used in this paper. The dataset consists of 1,030 hours of audio data and about 600,000 corresponding transcriptions, which have totally 6.7 million tokens. And here are some examples in the table. At the phoneme level, look into the distribution of English phonemes in CS segments and English alone. Besides, we study how pronunciations of phonemes and their differences influence the CS behavior. To compare the phoneme distribution, 39 English phones are considered disregarding the stress variations. We train a phoneme-level language model with the CS segments in our corpus, and the probability of unigram is used as the occurrence frequency. This figure illustrates the distribution of uniphones and their backgrounds. As we can observe, there's no apparent difference on overall tendency between the CS and English alone. In this part, we propose to investigate if pronunciation difference between the English and the Mandarin phones has an effect on CS behavior. We divide the 39 English phones and 66 Mandarin phones into 4 bins and shown in this figure. The y-axis represents phones in CS corpus and the x-axis represents the native English. And each quadrant is with top 50% or bottom 50% of the phoneme frequency. The IPA method and the data-driven clustering method are employed to measure the similarity between phones, respectively according to the left and right of the figure. It's shown that the majority of phones, 31 out of 39, fall into Q1 and Q3, which means their popularity are similar in CS and in native English. But there are 8 phonemes in Q2 and Q4. For instance, the is popular in English words, such as rhythm and gather. However, is not as frequent in Mandarin-English CS. For Q3, the clustering mapping has many phone pairs. It may be because of the limited using of the words containing them, both in the native English and the CS scenes. This limited observation shows pronunciation similarity aligns positively with the frequency of CS speech. One possible reason is that pronunciation th is relatively hard for Mandarin speakers to pronounce. Next is the analysis of CS on the word level. To measure the variation in word distribution, we extract embedded English words in our corpus and native English words. Numeric conversion in logarithmic is being done due to the huge span of frequency values. This figure shows the box plot of word distribution. It can be seen that frequency of CS words is less spread. The commonly embedded words in the code switching are also high-frequency ones used by native English speakers. Our heuristic hypothesis is that if a popular English noun or verb phrase can be pronounced at a much lower cost comparing to their counterparts in Mandarin, then it's more likely to be embedded. We measure the relative pronunciation complexity by the numbers of syllables involved on both sides. Average ratio of the embedded CS segments is 1.5, and for the 50 most frequent words, the ratio is 1.7. The average number of syllables in CS English words is 2.18. We can clearly see the ratio of syllable number. Most of them is between 2 to 7 syllables, and the ought to have a CS word with more than 11 phonemes is very small. Secondly, we implement a part-of-speech analysis on the code mix utterance to find out what types of words in terms of POS are more likely to be embedded. We use the Stanford log-linear POS tagger for Chinese and English separately. Top 5 English tags in the CS corpus and the monolingual wiki corpus are shown in this table. We can see the most common POS tags in CS corpus are nouns, which is close to half, followed by adjective, and percentage of other tags is relatively low. Try to find out what types of words are more likely to be embedded in terms of their meaning. We extract word embeddings directly from the BERT basic model for all CS words. They are clustered by a simple k-means procedure into 10 bins. By analyzing the top 100 frequent CS words, we found that nouns related to food, like chicken, cream, salad, are among the top ones. Other top clusters are related to music or weather in this figure. POS tags are the primary categories of words according to their functions in a sentence. This table lists the top 5 tags for the words preceding CS. This result echoes our above conclusion that nouns are the top category to be code-switched. In addition, adverbial particle is also quite common in front of CS, which is in concert with the observation that adjective and verbs are the second and the third tags. We pass the CS sentences to capture if there is general syntactic rules that may influence CS. We list the top 5 syntactic relationships between the CS segments and their context in the table. We can observe that most major dependencies between CS and the context are non-compound modifier, direct object, dependent, and adjectival modifier. CS follows certain constraints of the syntactic dependency from the matrix language, in accord with the matrix language frame theory to a certain degree. In this part, we check where CS tends to appear in an utterance. The starting position of a CS segment is normalized by the length of the sentence. 43.18% of the chance the CS appears in the body, and followed by in the tail and in the head. So for the phoneme level, we look into distribution and pronunciation of phonemes. For the word level, we analyze 4 aspects: distribution, pronunciation, syntactic rule, and semantics. For the context level, we study how positions of CS triggering words as well as the sentence parsing structure affect the CS. Specific results that we provide in each section can potentially help algorithm and system design to cope with CS. We reviewed some of these previous work in the introduction section. These metrics we proposed in this paper can be used to enhance CS data generation, CS language model adjustment, and CS naturalness evaluation, as well as end-to-end CS speech recognition.